The data looks convincing, but does it really prove anything? This dataset provides stronger evidence because the points are closer to the line of best fit. That makes predictions more reliable. This is the common trap. The data show association, not causation. So claiming cause goes too far. Remember this. Strong evidence supports association and prediction, not causation. Here is your first practice question. The scatterplot shows the relationship between advertising spending and monthly sales for several stores. Which statement is best supported by the data? You have 30 seconds. Pause the video and choose the best answer. Let's check the answer. The correct answer is B. The scatterplot shows a positive association between advertising spending and sales. Stores that spend more on advertising tend to have higher sales. Now let's see why the other choices are not supported. Choice A claims causation, but the data only show a relationship, not a cause and effect conclusion. Choice C says all stores, which is too strong. The points clearly show variation. Choice D assumes a definite reverse effect, but the graph does not support that either. So the best supported statement is the one that describes a tendency, not a guarantee. Correlation does not imply causation. Here is question 2. A marketing manager looks at this bar graph showing average monthly sales for two groups of stores. Because Group B has a higher average, the manager claims that higher advertising spending leads to better performance and should be increased. Which statement best evaluates the manager's reasoning? You have 30 seconds. Pause the video and think carefully. Alright, let's take a look at the answer. At first glance, Group B appears to perform better. The average monthly sales value is clearly higher. But the key question is whether that average truly represents how individual stores performed. When we look more carefully, we see that a small number of very high-performing stores, an outlier, could raise the average. That means the data do not show that most or all stores in Group B performed better than those in Group A. So, the statement that is best supported by the data is choice B. Choice A is not supported because the graph does not prove that all stores performed better. It shows only an average, not every individual result. Choice C is also not supported because it claims a cause and effect relationship without evidence. The data show a comparison, but they do not show that higher advertising spending caused higher sales. And choice D is incorrect because it simply restates the comparison without evaluating whether the conclusion is justified by the data. Key reminder. Averages can be misleading when a single outlier affects the distribution. Alright, let's take a moment to think this through. Look carefully at the information shown for stores A, B, and C. Each store reports an average daily sales value, but notice that the number of days is different for each store. The question here is not asking you to calculate a final number yet. Instead, it asks which method is best supported by the data. Be careful. Simply averaging the three values may feel natural, but ask yourself whether that approach reflects how much data each store actually contributes. Think about which pieces of information should carry more weight when determining the overall average. You have 60 seconds. Pause the video and decide which method makes the most sense. Alright, let's take a look at the answer. At first glance, it may feel natural to simply average the three values shown for stores A, B, and C. After all, each store lists an average daily sales value. However, the key issue here is not the averages themselves, but how much data each average actually represents. When we look more carefully, we see that each store is based on a different number of days. Store A includes only 2 days of data, Store B includes 4 days, and Store C includes 10 days. This means the averages do not all carry the same weight. Treating them as equal would ignore how much information each store contributes. With that in mind, the method that is best supported by the data is choice C. It accounts for the number of days at each store, ensuring that each store's data contributes proportionally to the overall average. Now let's look at why the other choices are not supported. Choice A is not supported because it simply averages the three values. This assumes that each store contributed the same amount of data, which is clearly not the case here. Choice B is also not supported. Dividing the averages by the total number of days mixes quantities that do not belong together, and it does not correctly represent how the data were collected. Choice D is incorrect because it uses only the highest and lowest averages. This ignores much of the available data and has no justification in the information shown. Key reminder: when datasets have different sizes, an overall average must reflect how much data each group contributes. On the SAT, averages are only meaningful when they are supported by the way the data were actually collected. Here is your advanced practice question. A survey recorded the average nightly sleep time of adults over several years. Take a look at the trends shown in the graph. Based on the data, which statement is best supported? Read each choice carefully. Some options may sound reasonable, but go beyond what the data actually show. Alright, let's take a look at the answer. At first glance, the trend in the graph looks very clear. Average nightly sleep time increases steadily over the years shown. Because of that, it may feel tempting to say that this increase will continue, or that adults are making healthier lifestyle choices as a result. However, the key skill being tested here is not whether the trend looks positive, but whether a statement stays strictly within what the data actually support. The graph shows how average nightly sleep time changed during the years shown. Over that period, the average sleep time generally increased. Importantly, this statement does not make any claims about the future, and it does not explain why the change occurred. It simply describes what the data directly show. This is why choice D may feel less impressive than the others, but that simplicity is exactly what makes it correct. On the SAT, the strongest answer is often the one that says the least, but says it with complete accuracy. For that reason, the statement that is best supported by the data is choice D. Now let's look at why the other choices are not supported. Choice A makes a prediction about future years. Even though the trend looks consistent, past data alone cannot guarantee that the same pattern will continue. The graph provides no evidence about what will happen next. Choice B goes a step further by claiming a cause and effect relationship. The data do not show why sleep time increased, and they do not justify a value judgment about lifestyle choices. Choice C makes a statement about all adults. But the graph shows only an average, not how individual people's sleep habits changed. Key reminder: on the SAT, even a strong trend does not justify predictions, causes, or broad generalizations. The safest and strongest answer is the one that stays completely within the limits of the data. Alright, before we finish, let's lock in the mindset behind evidence-based reasoning. The SAT is not only testing whether you can read a graph. It's testing whether you can stop at the right moment, the moment where the evidence ends and assumptions begin. First, what the data show. Data can support statements about what happened in the information you're given. In our examples, that meant describing what we could actually see: averages, trends, comparisons, and changes within the years shown. Notice something important. When an answer is truly supported, it sounds a little careful. It uses language like generally, about, or during the years shown. That's not weakness, that's precision. Second, what the data do not show. And this is where the SAT sets traps. The future. Even if a trend looks clear, like the sleep graph, the data only describe the past years on the chart. The SAT wants you to confuse a trend with a prediction. A trend is evidence. A prediction is a guess. Causes. The data might show that two things move together, but it rarely proves that one caused the other. The word, prove, is one of the loudest warning signs on the SAT. If an answer claims a cause without an experiment or stronger evidence, it's usually going beyond what the data can support. Everyone. This is another classic trap. A graph often shows an average, not individual results. So even if the average increases, you cannot claim that every person changed in the same way. Words like all, always, or everyone are dangerous unless the data truly guarantee them, which they almost never do. Now here's the SAT rule that ties it all together. The most tempting answer is often one step too far. It sounds confident. It sounds clean. It sounds like a conclusion you want to believe. But the SAT rewards discipline. The strongest answer is often the one that says the least, as long as it's completely accurate. So when you're stuck between choices, ask yourself 3 quick questions. Does this claim the future? Does this claim a cause? Does this claim something about everyone? If the answer is yes to any of them, and the data don't directly support that jump, that choice is probably not the best supported statement. Remember, evidence-based reasoning is not about being clever. It's about being careful. Accuracy beats confidence every time, especially on the SAT.